So what I want to do now is, in the previous section, we've done a little bit on QKD and teleportation. Now I want to kind of bring back and talk about this mythical quantum repeater, okay? Mythical, vaporware, a device that doesn't exist, that we don't really know everything about. And we can take some inspiration from the classical world, actually. So in the classical world, we know what repeaters are. We know what amplifiers are. And this is why I started with some definitions. So in the classical world, we use both in our networks, our internet, we use two devices, or two and a bit in a sense. So most signals, when we send a classical signal through a classical pulse of light, it will be attenuated in the channel. I can just put a straight amplifier in there and just take the signal that's decreased by half and amplify it back up to what it was, okay? When I do that classically, the problem is that when I've lost signal, I've also introduced noise. When I amplify it, I amplify the noise as well. I may have the original intensity of signal, but the signal is noisier. Typically, this doesn't matter too much because the whole point about classically, I only have a 0 and 1. So as long as it was 0 and 1, if there's a bit more fuzzy here, as long as I can distinguish these values, it doesn't matter. But sooner or later, as this keeps happening and happening and happening, as I keep amplifying and amplifying, my signal noise will go away. We'll get to a stage where there's no signal. The noise is dominant. So before you get to that, we bring in repeaters. And repeaters basically an amplifier, but they then go through and remove the noise. So if I knew my voltage signal was meant to be 0 and 1, but it got down to 0.25, 0.75, then my repeater could just recover the original signal. And one of the distinctions I want to really make in here at the moment is that in terms of terminology, typically when we talk about repeaters, and I've used the word here very specifically, optoelectronic, okay? So the key about classical repeaters is that we typically convert the light signal to electrons, we fix it classically, we fix it in electrons, then we emit it again. Rates out of some of these repeaters, some of the optical repeaters now, terabits. Okay, so we're back into reasonable numbers, okay? So I kind of enjoyed Shota's talk previously when he was talking about hertz again, okay? So classically, I want to talk about gigahertz and above, and a gigahertz optical repeater is slow. So, but unfortunately we know that I can't just do the same thing classically. I can't measure the quantum signal, okay? So classically what happens is that I measure it from the photonic signal, turn it into electrons and fix it. Quantum mechanically, there's this painful thing quantum mechanically say, if I measure it, I lose any of the coherences, okay? So we can't do that. But quantum amplifiers do exist. One of the nice things is optical amplifiers and quantum amplifiers are the same thing. So I can take an optical light and put it through an amplifier. I can recover an optical signal with quantum information in it back to its original intensity, okay? But I've added noise. Actually, going further, and do I say it here? We even have noiseless linear amplifiers, okay? They add no noise to the signal, okay? There's a gotcha. They are probabilistic. But here are them. When they work, it's perfect. When they don't work, goodbye. Probably not very good for networking, is it? Sorry, no signal, no signal. Oh, yep, that one works. So what that means is that when we start thinking about repeaters, they're going to have to be very different than their classical counterparts. We see you sneaking in the back. And currently, in a sense, when we talk about repeaters, okay, typically most of the community is focused on repeaters just being a source of generating entanglement between two parties. Does it have to be the case? No. Okay. Classically, do I have to have signaling between two nodes? We have broadcasts. So quantum mechanically, I can make broadcast repeaters, okay? The question really is, at the moment, we're not that far ahead. So the real question then is that what's a requirement in a sense, okay? So we need to think about what we really need to do here. What else do I want to say here? Yeah. This point. Repeaters need to fix not only channel loss, but any other areas that go along. So most of you know optical fibers, or you have seen optical fiber. So I'm an experimentalist in the back. What happens when I send polarization photons down optical fibers? The polarization changes. And actually the polarization reference with each other changes, okay? So optical fibers not only have loss, they have birefringence. There's a lot of nasty effects in there, okay? And there's coming here, there's one reason why when we're doing a lot of stuff in optical fibers, why we use time bin, okay? Or frequency bin. We tend not to use polarization over 500K. Some fibers are polarization preserving. So it depends really on what the infrastructure is, but the infrastructure we have at the moment for fibers is based on the telecom world, and it wasn't built for our quantum world. So we're trying to use dark fibers that already exist. And probably the most important point here, and it's one of the things that Shota kind of pointed out a little bit, but it's really important to mention here, quantum repeaters, quantum networks do not exist without a very efficient classical network sitting behind them, okay? And I really want to emphasize this. And I want to go even further, and it may shock you, okay? So you're here, most of you here are probably looking at networks and various things like this, okay? Quantum networks, given the focus of this conference. I will say at the moment, you're doomed to failure. Not because of the quantum mechanical aspect. The problem at the moment is that our classical networks are too slow. We talk about Shota and his TCP, IP, UDP. What are the timescales for sending packets with UDP or IP and various things like this? Hundreds of microseconds? Okay, how far does light flow in 1 millisecond, okay? So suddenly what happens is, I want to send a signal between myself and Shota there. We're only 10 minutes away. He gets my quantum signal in 20 nanoseconds, okay? He gets my classical message 1 millisecond later. So what that means is that with these quantum networks, the entire infrastructure behind how networking is done has to be changed. We can't just say that the classical network we have at the moment is going to support this, okay? Because it's not. Because at the moment, I think at the moment is, if I plug two network ports in here, probably this laptop communicating to someone else's in here, maybe bouncing back through our main campus and back down. So this classical networking speed, this classical network is something that, as a community, we're quantum people. Classical is there. It's a headache, okay? So don't assume this. And then when you look and you say, oh, there's only a little bit of classical. Classical's easy, okay? Okay, but what happens when 99% of what you're trying to do is classical, okay? 1% is quantum. Almost all the rest of what you're trying to do is classical. So classical actually dominates every operation. So teleportation, the example I gave, one entangled pair, two classical bits. Where do we start doing these repeaters, entanglement distribution, purification, swapping, classical bits, classical bits, classical bits. And many years ago, when I was young, okay, and crazy, we did a simulation of a network based on a telephone network at that stage, okay? And one of the things we said is that, let's take a 500,000 node network, forget about purification, but we just wanted to have, we put probabilistic entanglement between these things and then did classical communication and tried to work out who knows what. The number of classical messages that we had, if operations failed or saying who knows what at what particular time, meant that we were seeing hundreds of thousands of classical messages trying to catch up, okay? So the classical networking is a huge headache. I'll come back to this in a moment, but this is a quantum workshop, unless David's changed the title to remove classical from it. So let's come back to the concept of a repeater. So really what we're going to do is we're going to take some long channel, length L, and we're just going to subdivide this into n smaller pieces. So what I should say now, and I said in the previous lecture, these lecture notes are now on the web, so you can download them even here for the rest of the course. I think art etiquettes have gone up as well, so it means your note taking is limited. How do I want to encode the photons that go through this? Polarization, time bin. Sorry? Yep. I mean, single rail, dual rail, continuous variable. I mean, these things all make a difference and they all change the scalings in a sense. And so the ones I'm going to concentrate on, I'm going to, for the rest of what I'm talking about, I'm going to skip CV repeaters. If people want to chat to me, find me offline. They're much harder beasts to actually look at in a sense. So encodings, single rail, presence or absence of photon. Looks like twin field QKD, correct? But you'd probably be surprised to hear single rail encodings for repeater designs were there 20 years ago. So single rail repeater designs, entanglement distribution, came well before twin field QKD. Then we didn't like them because there were only one detection event. They were less efficient when things were noisy. But then we moved to dual rail, time bin, or where you measure a photon on one slot or another. So basically, these encodings make a real difference. So if I think about my channel, and I'm just going to write the success probability for the photon getting through as ether minus L divided by L0. L0 is the attenuation length of the fiber. Free space, optical fibers, 22K, or 0.17 dB per K, okay? Free space, depends on how cloudy the day is. And given I'm a New Zealander, we can have perfect conditions to absolute fog in the same day, so the communication channel can change significantly. So what happens is that, just crudely speaking, okay, if the probability of getting this through is ether minus L divided by L0, if I want a link, then on average, I've got to try 1 divided by P to get it through. So this is going to scale as e to the L, the number of times to try is e to the L over L0. This is averages, this is a pretty crude measure. When I break it into segments, okay, these segments are now ether minus L divided by NL0. And so it comes down to now, how many times do I need to try? And it depends on what operations I have. So let's start without a memory, okay? Without memories, this one has to succeed, this one has to succeed, this has to succeed, this has to succeed. So basically the number of attempts is going to be e to the L over NL0, or to the power of n. Guess what? The same number. So without a memory, there's no gain while you're waiting, in a sense. If we have memories, then it's going to scale, and the constant in front, you'll have to work out yourself. That's why I put question marks. It's going to scale as like e to the L over n L0, okay? So basically, once you have a memory that can store them, this one's failed, this one's worked, this one's worked, this has failed. Rather than throwing everything away, now I just tried this one again. And so that very quickly, you get to cage, once the sorted memories, everything works. Once everything's worked, swap, get your long scale. And what this constant should be out in front? Work it out. But the key really is, the scaling here is really, really different. And that's the basis behind repeaters in a sense, okay? That is the key. We're not talking about the repeaters stuff yet, but it's kind of this change in scaling. So being able to store so that when this one works, you don't have to reattempt. Because let's say this worked, this worked, this worked, this one failed. Without the memory, I throw everything away and start again. Then maybe this, and this one worked, but not this one. And so the chance of getting everything to work is lower. While if these three have worked, I've stored them, I try again, it succeeds, all four, you get this improved scaling. So one of the things that I'm trying to do, okay, and you probably wonder why I put this mythical 100 factor in front, okay? The probability of success, I said, on average was roughly 1 over, okay? If it was 100 times, the chance is not there, it's very, very small. So normally you'll have to work out some threshold. How many times are you prepared to try before you start again? And there's a number of groups, including David's here, Rod's, Delft, where these thresholds and cutoffs have been put in a sense. But I mean, crudely here, I've just said that I'll try roughly 100 times. And then once they've all succeeded, we join them together, you get your entangled pair you can use for teleportation. That is the basis behind long distance quantum communication. It is that simple. Now the reality is how we make all the components work together. And that's kind of what the overview we're going to start taking this is we now need to start drilling down into all of these components. And we need to look at entanglement distribution, entanglement swapping, purification, and then some scalings, okay? The order here may not be what you expect. Many people expect that distribution you have to do first, okay? You can't do swapping or purification without distribution. But why do I do swapping before purification? Purification may not be necessary. Swapping is. Let's say I've got very, very good pairs, okay? It may be at the end, I only want a state out with a fidelity of 95%. And I've got 50 nodes and I can get that fidelity without purification, don't purify. So purification is potentially optional, okay? But if I go to double the length, maybe it's necessary, so you have to be careful. Entanglement distribution, I'm going to kind of break into kind of 3 categories in a sense, okay? And the way I'm representing this here, okay, is I'm always thinking about some cavity or some memory where there's an interface to some photonic mode. And the emitter scheme basically is I have this qubit, this memory emits a photon of light. This emits a photon of light. They interfere on the beam splitter. I end up with entanglement. That actually is probably the most, under all the proposals at the moment for entanglement distribution, that's the most popular in a sense. We'll come back to it, but I can do the reverse, okay? I could take an entangled source in the middle and send them out to either node and then absorb the photons. So there's a number of combinations of this, okay? And what I'm going to do just for convenience, mathematical convenience here at the moment, I'm going to say this kind of Alice node generates a state like GH plus EV, okay? It's an arbitrary thing, but it generates a maximum entangled state. So let's go through how this protocol works, okay? Both emit, so I'm going to have a state like GH plus EV on Alice's side, GH plus EV on Bob's side. You can write all the terms out, and this is one of the nice reasons for using a PowerPoint presentation, rather than having to write all over the board. We can then put this through a polarizing beam splitter here, and what I want to point out is that in this case up here, every photonic mode has either H or V polarization. But when it comes to the polarizing beam splitter, I still have some cases where it's H and H, V and V, but I have other cases where we've had bunching. Both polarization photons now end up in one mode. HV in one mode, nothing in the other, or vice versa. At that particular stage, what do I want to do? And what we do is, crudely speaking, is that I just want to measure one photon here, okay? One photon in either mode. That will cancel this photon. This doesn't have a photon in either mode, so we won't see that. We won't see that. Therefore, I'll only see the information coming from HH or VV, but I need to raise information. So I don't want to measure on the HV basis, because if I measure the H basis, I collapse the GG. As far as I know, GG is not entangled. But if I measure the diagonal basis, okay, for both photons, I could end up with GG plus EE for both measuring the diagonal, diagonal, anti-diagonal, anti-diagonal. What if the result is DA? Diagonal in one, anti-diagonal in the other. What's the state? GG minus EE. So what happens here is this protocol for entanglement distribution without loss, okay, works a maximum of 50% of the time. Because the chance that I have in the wave function, I am discarding these two terms. Okay, I'm measuring one photon in this mode, or photons in this mode, or those. That's only 50%. So entanglement distribution is now probabilistic, and it's the one advantage that we have in optics. It's heralded. I've said we get GG plus EE when I measure diagonal, diagonal, okay, or anti-diagonal, anti-diagonal. So when I put channel loss in, okay, so one of the nice things of these calculations is channel loss is easy to handle, okay? When I put channel loss in, the photon's lost in the channel. That means that photon is not available for the detector. So if I say channel loss for the entire length here is e to the minus L over L0. And the overall success probability is the probability of losing a photon here, the square root of eta. The probability of losing a photon here, square root of eta. As I'm a theorist, I can assume we have perfect detectors. And then we're going to have the square root of 2 from the post-selection. So this is going to scale as eta divided by 2. So now if eta is 0.6 or 0.7, great. If eta is now 0.01, because these distances are too long, then the chances work is very, very small, correct? So the whole point is that for most of the repeater schemes, there's actually an optimal kind of distance you want the repeater stations apart. Is this 1K? Is this 100K? It depends on your system, but we probably don't want to do it for 1,000K. So the question is, can we do better? Okay, let's come back and think about twin field. So instead of encoding a polarization, now think your system, now think that Alice emits G times 0 plus E times 1. No photon, one photon. the twin field kind of paradox, or the twin field kind of regime. We replace the polarizing beam splitter with a normal beam splitter. And what you find out is that you end up with a state like this. Where's this other rearrangement? So in this particular case, what we do is that I have certain cases where I have one photon in one mode, nothing in the other, or vice versa, with a certain Bell state. I have other cases where I have no photons or two photons. So I'm going to use photon number resolving detectors, condition on detecting only one photon. If I detect only one photon, I get either this state or I get this state. So I get GE plus or minus EG with a probability now that is not eta over 2, it's now the square root of eta over 2. Why the square root of eta? Because basically a single photon only travels half the distance. Why do I not like that scheme? Better success probability. Dark counts on my detectors, other noise sources. So basically, when I'm detecting two detectors, the chance of both the errors is small. When I detect only one detector, where else can that signal have come from? And so when the original repeaters come up, this was one of the original repeater schemes, entanglement distribution schemes. But it was thought to be more noisy, okay? Therefore, we moved to the other scheme where we did coincidence detection, because there the states you get out of higher quality. So then the question is, what do you want? Do you want better success probability? Lower quality? Lower success probability? Better quality? You have a choice. So there really are kind of three kind of conceptual schemes, okay? There's a emitter-based scheme at the moment. What we call the receiver kind of schemes, where you start with an EPR pair in the middle and you go out. One thing I want to point out here is that I've drawn this as in the photon comes and interacts with the memory is then detected by a separate detector. That is not absolutely necessary, okay? But what I need to, if you have a memory there, I have to have some way of heralding that the photon went into the memory. It's a choice, okay? So maybe the memory has a transition and you can see it some way, but I need to confirm that. Or I can go for half and half. Emit on one side, receive on the other. In some of the areas I work, I mean, in the NV centers, overseas, this emitter model is a common one. In Japan, this absorption model has been done by people like Kosaka-san up in Yokohama. So basically, it's a choice, okay? Choose the one that you like, choose the one that works with your experiments. So of these three basic plans, okay, which one is better? So when I think about this single rail or dual rail encoding, okay, I can just write down how the scaling is, okay? Emitter, I know square root of eta for single rail, eta for this. The same for the receiver kind of model or absorption model. When I come down to one of each,
like less noise.
Sorry, say that.
Single rail has less noise.
It's seeing less effective loss. But in this case, it's not clear. It could be the square root of eta. It depends on the scheme. Because the problem in this case, okay, the reason I'm saying it's not clear, in this case, the photon travels half the distance, okay? Either a photon's traveling from here in the middle and no photon from here. In this case, I create a singlet state like 1, 0 plus 0, 1. Photon travels half the distance, okay? In this case, The photon seems to have to travel over the entire length. There's no half in here. The photon, if there is a photon, there's no photon, it doesn't travel. But if there is a photon, it travels over that entire length. So sees ether in a sense.
In the middle case, we have two particles, right?
No, it could just be, it's a Bell source. It could be a single state. It could be one, it could be a source of light that produces one photon, 1, 0, minus 0, 1.
Also a quantum dot in a beam splitter.
Yeah, quantum dot in a beam splitter. Yep, exactly. So that's kind of why when you're thinking about entanglement distribution, you always need to think about what your scalings are. Are these the limits? Can I do better?
Latest one has the square root of eta. PF could be doing
So you think square root of it is the best?
no,
I will just say, chat to me afterwards, I'll say, actually, maybe you're right, maybe you're wrong. One thing I haven't told you is, what are the ground rules, okay? So what would happen if I had a scheme, okay, hypothetically, where instead of just having this, I had this and this combined. So I start putting more objects in the middle and I start doing some funny business. Maybe you can get slightly less than eta, okay? It's square root of eta, okay? But then it's becoming a little bit ridiculous in a sense. So I may gain a little bit, but the complexity, if we're to build repeaters, and kind of what Shoda was kind of showing in that, and then Rod, we're not going to be building one of these. I'm going to want millions of them, okay? These things are going to have to be simple. They're going to have to be reliable. So one thing that I just want to point out, and I'm not sure whether Jackie's going to talk about tomorrow, I've always been talking about entanglement distribution schemes here based on qubit encodings, okay? This stuff can be naturally extended to qubits. So we can do qubit repeaters if you want. Metrics, performance. What do I want? What do you want? A shopping list. Fidelity. Entanglement rate, throughput. Success probability, yield. Entanglement length, the maximum length at which I can distribute entanglement. Entanglement cost. Q bar. Which one? Sorry? There's no right answer, okay? The reason being, it depends on your application. If I'm working with QKD, maybe Q bar is a good answer. If I'm working like Shoda was talking about, trying to connect two data centers together, fidelity is really, really important. I'm going to have to be fault tolerant at 99.9%, okay? So these metrics are fluid and they'll change depending on what you're doing. And that's just the thing to keep in mind. Why do I care about metrics? Is it too early? I care about metrics because they define the reliability and usefulness of the links. So what happens is that if fidelity is most important, okay, I probably want to use a dual rail encoding because it chops out some noise and various things like this, okay? But if it's the rate, being able to go from eta to the square root of eta, I definitely want single rail. So entanglement distribution between adjacent repeater nodes or between adjacent nodes is the first step in really starting to think about building repeater networks. The next step is very simple, and this is kind of why I went through in the previous one. and define some symbols. Entanglement swapping, okay? Very bluntly, entanglement swapping is basically take two bell pairs, do a C knot in the middle and measure, okay? Or bell state measurement, depending on how you want to label it. So in this case, we have a link between Alice and the repeater node, another link between Bob and the repeater node. We take these two qubits that are in their memories, we do a C knot gate, we do the Hadamard, we then do the measurement, okay? And then I get an entangled link at longer range. What's the problem? Or what's the headache? And I kind of skipped over it previously, okay? In any of these protocols, I've measured one photon and one photon. I have to communicate to Alice and Bob the result. If I don't communicate, they don't know whether to keep or discard the pair. That's in the middle. In this particular case, same thing. Was a photon actually detected? Bob needs to know. Because maybe Alice detected, Bob didn't. Classical communication. Classical communication is required here as well. In this case, because Bob has to tell Alice photons received, entanglement generated. So in entanglement distribution, inherently, we are sending classical messages saying success, failure, or could be success and it's this bell state. When I go to entanglement swapping, I'm sending two bits of information. Okay, so entanglement swapping is basically teleportation. We're teleporting. That's your entangled link for the teleporter. And then basically entanglement swapping is allowing us to swap this part here moves to here. So entanglement swapping is a form of teleportation.
Maybe I'm thinking too much about QPD, but if we want to use this entanglement, we need that per day swapping. Alex and Bob need a quantum memory, right? Just throw the other.
If you want to use it for anything else, yes.
Yeah,
other than QKD, yep. Either. Carry on, please.
So you need the memory to last as long as the.
Exactly, and this is one of the big headaches with memories. So the question is, this is just a simple case, okay? So how long do the memory lifetimes have to be? So suddenly we're talking about some operations where this thing may be hundreds of microseconds. Memories have a T1 and T2 time. I probably need the memory time probably to be 100 times the worst one. So therefore I need memories at milliseconds or seconds. And that really becomes a challenge. And as these things expand out and out, those memory times are not chosen just by the adjacent links. They end up being the time over the entire network. So sometimes these memory times may have to be hours. So really, that really is the thing sitting in here, okay? And thanks for bringing it up. For anything other than QKD, you have two choices, okay? And maybe you have two choices, maybe you don't. One, maybe you put memories in, okay? Store it. Can I just use it straight away? Actually, entanglement distribution, no. Entanglement swapping, potentially. What I'm waiting for in entanglement swapping, I know I had this link. I know I had this link. What I'm waiting for are these two classical bits. This we call the Pauli frame, and maybe the operations I'm doing on this side, I can fix the Pauli frame later. So it's possible I could use them in advance, but if I do anything that doesn't commute with the Pauli frame, I'm dead. Okay, so basically there are special cases where I could use that entanglement immediately before the classical information arrives. But very special applications or very special operations. As in, I can do any Clifford gate, okay? So I can put this into a quantum processor and do any quantum computation you want, as long as it is the Pauli gates. It could be a CNOT gate as well. If you add the T gate, goodbye. I mean, I don't recommend it, okay? But what I'm saying is there is potentially that choice. But then the question is, do we build a system for that very special case? No. So basically, we're going to require the memories. We're going to do this so it can do an arbitrary task. Now, this is a little bit laborious, okay, but I want to run through the details. So we're going to consider this link and this link. I'm going to write them in this tensor product. And these are in the notes that you have online, but I just want to run you down because it's important if you've never done the calculation, just to do the entanglement swapping. I've just broken the states up. I do the CNOT gates. I say measure qubit 3 in the GE basis, measure qubit 2 in the plus minus basis, just so you can see how the states are collapsing over time, okay? How the signs come about. I won't spend any time really going through more of these details, but this is just, there's a large number of cases, okay? But you really need to get familiar, if you think about repeaters and various things like this, just going through swapping and seeing what's happening at every step. Because these CNOT gates are not hard, but by the time you start writing many of these down, you need to get this intuition. So the swapping operation, just to emphasize, gives us the bell pair between Alice and Bob, with the repeater station in the middle out of it, okay? So once this entangled swapping operation is done in the middle, that central node is free to do something else. So what you can do, you could generate entanglement between here and here, here and here, here and here. Do swapping all at the same time. Alice and Bob get their magical bell pair. Now, let's think about scalings. So the previous example, when I wrote on up there, I was assuming perfect bell states, okay? What if this fidelity, this is not a perfect bell pair? What if this is a fidelity, say F, okay? And everyone has fidelity F, okay? So when I do swapping, Alison, the fidelity of Alice and Bob's pair is now scaling as F to the power of n minus 1. You may say, this is not a problem, okay? And I'd be a very nasty person, okay? I say, oh, fine. Give me a fidelity that you think you can do in your lab. Oh, 0.999, okay? I think, fine, I'm gonna have 10,000 nodes, please. 0.999 to the power of 10,000, that's less than a half. You have no entanglement. If it's 0.99 and I'm doing 2 or 3, brilliant, that's what I'm saying. Depending on the scaling in a sense. So the reason I put this up is just doing entanglement distribution and swapping still leads to an exponential scaling. Repeaters have to overcome exponential loss scaling. Over exponential scalings. It's the whole premise of them, okay? They've got to make everything polynomial. This does not do it. And just so you can see what happens, okay? Depending on how many links you put in there, you can kind of see how the scaling goes in, okay? And so that basically at the moment, putting these links in, if you have perfect links, you can get arbitrary scalings that you want. But we need to be careful. And I do like performance in arbitrary units, so I don't have to write down hertz or arbitrary numbers in a sense. But is this realistic? So for our experimental colleagues, how many of your labs are perfect? So you're telling us poor theorists, that experimental reality is different than our mindset in a sense, okay? So the whole point is that in the experimental labs, there are other noise, there are other noise sources. Things are not perfect. So basically, we've got to fix this. And I want to look at imperfections, okay? So I just want you to see what happens with imperfections, okay? Actually, a little bit of detail. So a pair of fidelity F, I'm cheating, okay? I'm choosing a rank 2 Bell state, so a mixture of 2 Bell states, not the Werner state. The reason for the rank 2 Bell state is that it's simpler right on the board. And then I'm going through doing the swapping, looking at what the initial state is, and writing down all the terms and saying our final state that we get out is basically this of one Bell state plus this of the other Bell state. We started with the Bell state of fidelity F, okay? And now I've roughly gone to F squared. Unfortunately, F is strictly less than or equal to 1. Therefore, F squared is always less than F. So if we plot your initial fidelity versus the final fidelity between Alice and Bob for the swapping operation, that's just if it was a linear line, you lose. Your fidelity is always approximately S squared. If you use Werner states or Bell state plus white noise, similar behavior comes out, okay? You never end up with a curve. I did hope for many years that I could do this. No. So here, what this is saying is that basically, when you start with a pair of initial fidelity F, the final fidelity you get is always worse than it. And you can kind of see if your pairs aren't initially very, very high. If you start with a pair of fidelity 0.8, when you finish, your fidelity is about 0.65. This quadratic hurts, correct? I mean, yes, if my pair, I'm initially starting with this 0.99, and that's what's available in the lab, then I go to 0.98, okay? So up here is kind of a very nice regime, if we can get to it. But the reality is that for most of what we're generating in the labs, we're sitting below that at the moment. That means we had to look at purification. Purification, error correction, some way to cure the effect of your local gates, because every C0 gate we do is noisy. Entanglement distribution is noisy in terms of the states are not perfect. So I'm just going to take you through the earliest, most simple purification protocol, okay? Which is basically between Alice and Bob, take 2 pairs, C0, measure in the 0-1 basis, measure G&E, measure G&E, classical communication. Alice tells Bob she measured G. Bob says, I also measured G. They keep the signal. Even parity result, they keep. Odd parity, start again. What I want to emphasize here is again, classical communication. Classical communication between these repeater nodes. It's happening everywhere. So let's just, again, the notes are around so that you can see them, okay, online. But let's just take a state like this, apply the C0 gates, and then just kind of, let's just scroll through the mechanics and see what happens, okay? And what I'm doing, which is a cheat, because I really don't like working in density matrices, okay? So I'm going to write, I've got two pairs like this, so I'm going to write out the 4 states, and one pair is a state like psi plus, psi plus. Then I have another state like psi plus, psi minus, or psi plus, phi minus, and all 4 of these. So I can just look at these, apply the CNOT gates, and really see what happens, okay? And then I can put the state back together, okay? And what happens is that when you do this, you end up with this particular state at the bottom, okay? Then I say we measure qubit 1 and 2. If we measure G, G, or E, we have the state phi squared times the state we wanted plus this. If it was G, E, or EG, we have F times 1 minus F with an equal mixture of both of these. So one thing is, and this is an important point for you, entanglement distribution probabilistic. Swapping, in principle, can be deterministic. Purification, probabilistic. So when we measure even parity, we keep the state. If I measure odd parity, goodbye. Please do entanglement distribution again. Please potentially do entanglement swapping again. Do everything you need to get back to this particular state. And so what I want to point out here is that you end up getting the state down here, and classical communication of the result GG or EE is required. The notes are there so you can see the details, but I think in terms of notes, it's occasionally handy to be able to go through it step by step so you can see what's happening. So what this means, okay, I've done purification, it's been successful, okay? So I do 1 round of purification and I've got my magical Bell state back as I start here with a Bell pair of fidelity 0.6. Successful purification takes me to roughly 0.7. I do another round, I get to 0.8, 0.9, and I go up step by step by step, okay? At each step here, I need 2 Bell pairs. And so if there's 3 rounds of this, the last round needs 2 successful. The before then needs 2 Bell pairs for the purification. So actually 3 rounds means you've got at least 8 successful events you require. So this is the purification curve. This is the output fidelity, input fidelity versus output. What's the probability of success like? It's greater than 0.5, but it's still slow going.
Has it been done experimentally? And if so, how many times has it been chain linked?
I think purification has been done experimentally in optics many, many years ago, but I don't think it's been changed at all because we don't have memories. I can do one case just with optics, without memories, and then measurement. But as far as I know, no one has done purification through multiple rounds. I know a number of groups who are working towards it, but it's hard. And when I say the success probability here is 0.5, I'm assuming you have very good detectors in the lab. Actually, yes, I know some of my colleagues have 99.5% single photon detectors, but they're exceptional. A lot of optics groups who are not using cryogenic stuff are running detectors at 50 or 60%, okay? So what this means is, in a sense, is that you can kind of see how it can step up and up. So this is a way that entanglement swapping decreases my fidelity, entanglement purification increases it, okay? But slowly. So one of the questions is, I want to work here if I can. So it's really important that experimentally I try and generate as high fidelity pairs as I can. Because basically, if you're not going to generate high fidelity pairs and you generate low fidelity pairs, you're then going to have to go up you're then going to have to do purification and go up the staircase. And in a sense, entanglement distribution and using eta rather than the square root of eta, okay, that's a hit, but it's just one operation you're retrying. Here, you're doing many, many measurements, much more classical communication. Is this the only way to do purification? No, there's a zoo of schemes. I showed the original one, but work we did with Rod and Kindamoto and that. I can say when Rod was a young man, okay, 2009. So as you see, over 15 years ago, we looked at different ways. You've got these entangled pairs that may have different fidelities. What way do I put them together? Do I put high with high and then I come down? Do I put the lowest together? How do I schedule these, okay? And so we went through and looked at different structures, symmetric, pumping, which was a scheme kind of put out by Lucan and that, greedy schemes, banded schemes, and we set out to just kind of work out what's best. And so this reference down here will take you back through a number of the strategies, okay? And is there one that dominates over the other? No. It depends on, again, experimental conditions and various things like this. I mean, maybe in a sense, in your experiment, you only have access to 2 bell pairs at any one time. If you've only got 2 bell pairs, in principle available in those nodes, you have no choice. You have to do entanglement pumping. You keep one pair, you bring a new pair in, and keep trying to pump it up. Slow, but it may be what your resources give you. So one of the things that I think you'll kind of seeing is that we're potentially doing many, many rounds of purification, okay? Every round of purification means one classical message. I don't like that. And that's because all these schemes here are based on variance. But it doesn't have to be this way. Purification, entanglement purification. Another name for it is error detection. So I can go through and replace the purification codes with error detection codes, and then take 5 copies of the state, do gates between them, and in one round time, in one time step, if it's successful, get a much higher purified pair, okay? That works. It works very effectively, but there's a problem, okay? Basically, when I had just 2 pairs, okay, my maximum fidelity that I could get out was basically 1 minus 2 epsilon, where epsilon was the error of a C0 gate, okay? In this case now, I may have 10 C0 gates, or 20, depending on what I do, okay? That means now my maximum fidelity could be 1 minus 5, 7, 10 epsilon. I get one time step, but I now need my gates to be much, much higher quality. And if you're doing error correction, error detection, that's going to be the case anyway. So let's just put all the 3 pieces together, okay? You can kind of see the schemes. And I don't know why, but I seem to have just, this figure here, I think should actually be entanglement distribution, okay? Or maybe not. Maybe I know what I'm thinking. It's a problem when you write lecture notes a month ago. So what I'm going to say in this scheme is I'm going to have Alice, an intermediate node, and Bob. The pair that I'm going to generate is not good enough, okay? I'm a very nasty person. I'm going to want 0.99, and you can't give it to me. So the question is, what am I going to do? I'm going to generate between Alice and this node. I can generate multiple entangled pairs, okay? And do purification initially. And then I can do swapping, okay? Or I could generate a pair and a pair and do swapping. Then do, so swapping, then purification. So I have a choice. Do I purify, then swap? Do I swap, then purify? Any guesses? Swap, then purify? Why?
Like swap will also introduce some noise, so you can purify that and then.
That's exactly what we thought ourselves. So let me just explain the figure to you, okay? Initial fidelity, final fidelity of Alice and Bob's pair. I'll just highlight a couple of curves to you to start with. This red curve here is, it's purification then swapping. The other one is swapping then purification. So swapping first is detrimental. Why? Higher, yes, it's exactly it. So this fidelity, when you're taking a state that's not perfect and you're making it even worse, and then it takes longer to come back. And just to finish this figure, so here, and we use this a lot of the time in a number of our early calculations, we identified points where swapping, purification plus swapping, the initial fidelity and the final fidelity are exactly the same. And so when you're trying to do some calculations, what that means is that there's a natural stable point for the fidelity, and so calculations scale easy. That's for a mixture of two Bell states. What happens when I have the Werner state? White noise plus Bell state. Good luck. And this is a crowded figure, okay? I'm looking here basically at a curve here. So I'm saying what the 1 round, 2 rounds, 3 rounds of purification. But the curves really are to look at this curve here, okay? Which is 3 rounds of purification plus swapping, okay? And so that if your fidelity is basically less than 80%, with the Werner state, you're going to have to do more than 3 rounds of purification. At 2 rounds, you just touch the curve. So, 1 purification protocol, the mixture of 2 Bell states, 1 round would seem good. This case, 3 rounds. Actually, in the lab, you have neither of these 2 states. So one of the things that you need to do, and it's what we spend a lot of time over the years doing, is looking at what the sources that you have, what the states you have are, and then tailoring this purification protocol to what the reality is. I mean, white noise people like mathematically because it's the easiest to handle, but it's the least likely you're going to have in the lab. Okay, you're never going to have a mixture of 2 Bell states, but by being able to tailor this, you'll be able to move somewhere between these 2 regimes. Given we have a little bit of time left, I do want to move into just talking about a few old components, okay? And I chose some old examples, okay? To say, what do I believe you need for a quantum repeater, okay? You need either single or entangled photon sources, okay? Potentially. Or you need a source that entangles a photon with a memory. you definitely need single photon detectors. You need quantum memories. I don't think anyone's going to argue that I need frequency converters, diamond NV centers, ion traps. If I'm lucky enough to work with erbium, I don't need a frequency converter. But I added this mysterious object in here called buffers. Sorry? So a memory is normally an object that stores something for a very long time. But one thing that I'm likely to have to do in all of these circuits is I'm going to have to resynchronize photons or delay them by a very short amount of time so that they interfere on beam splitters or various things like this. You probably don't want to use a memory to do that. So you're going to want something that you can vary the time and delay the thing by a few nanoseconds or various things like this, okay? Because as your fiber goes through the ground, the temperature goes from -20 to 20. The fiber length changes. You have to redo this. There's large numbers of single photon sources, or that you can start using for think about this. I mean, one of the things that I kind of like is the defects in diamond and various things where I can emit photons from them. That's just as equivalent in a sense, okay? Detectors, this is an old one. But what I'm saying is at the moment, the detection problem is pretty much solved, okay? When I started my career, okay, many years ago, before I was completely white, our good single photon detectors in the lab were 15 to 20%. We had miraculous ones, okay, that were 50%, but very, very high dark counts. Now you can buy off the shelf 85 to 90% single photon detectors or even counters, okay? And what we know from the quantum, leading up to the quantum computing community, people like Quantum and various others, is they now have detectors in their labs at 99 point something, okay? In the telecom regime. And it's not just one company, there's several companies that are now talking, the numbers I've seen recently are them 99.3 to 99.7. And they can go higher. Problems effectively solved, I think. Okay, yes, give me 99.99, but I'm not greedy in a sense. There are other things that we need to fix first. When it comes to memories, I'm not a memory expert. So some of the other people in this conference will talk about memories, but basically memories has to be long-lived, okay? And so one of the things that we talked about, we're doing this in purification and entanglement swapping. When I do 3 rounds of purification, okay, that means there's 3 round-trip classical communication times. That means the memory has to be 3 times longer, correct? And that was on 2 adjacent nodes with 1 station in between. Now think about that. This is now, there's 20 nodes in between, and I need 3 rounds of purification. These times start hurting in a sense. So memories, there's a lot of work in there, okay? If you want a really long time, it's probably nuclear spin. Probably, okay? And how long do I need? Is a millisecond good enough? A second? An hour? So depending on the physical systems that you're playing with, there'll be demonstrations in all of those regimes, but it really depends upon what you're doing. I mean, if you're going to try and use these memory-based systems for distribution over 1000K, you're probably going to want memory times of minutes and above. So the buffers of this is some stuff we did at NTT many, many years ago. And it's basically just a simple crow where what we're doing is by controlling the temperature, we bring a photon in here and we just put a controlled delay on it, okay? This one was a little bit lossy, but we can basically just delay the photon by 100 picoseconds, 500 picoseconds, 3 nanoseconds, and it's controllable in a sense. Frequency converters, up conversion, down conversion, conversion everywhere. Do I want to up convert? Do I want to down convert? Again, it depends partly on how your entanglement distribution is working, okay? So if you're using NV centers and these are going into telecom fibers, then I need to go from 650 to 1550. But do I really do frequency conversion? Or do I put a bell station in the middle and distribute telecom-based entangled photons and then do a down conversion? I mean, there's choices, and this is all part of the design apparatus in a sense, okay? I can't say what's better because, again, we found different cases where they all work.
Sorry, what's a crow in the last slide?
Okay, so a crow basically, it's an acronym, but basically it's a cavity where basically there's a lot of holes sitting in it. So it's just think of it as a photonic crystal cavity in a sense. But there's holes that allow you to really slow right down or store objects in there in a sense. I can't remember what the acronym is. I can find it again. It's been too long since I looked at it, but it was one of the ways that part of the photonic crystals community were building cavities to actually store things in, and there's potential of some of these things that you could actually put a diamond center or something on near it and then couple light. One of the problems has been, depending on the material, currently they're still quite lossy. And I always worry about loss. Anything more than 3 dB is a disaster. So frequency converters, I do want to put up the sheer fact that I believe in a lot of our repeater systems, we will probably need some simple linear optical circuits, okay? If I can do things in linear optics without having to do processing in the memories, do it, okay? Just because if I can stop having to write into a memory, do something, write it back out of the memory again. See you, Shoda. So these, I mean, and this is not a comprehensive list, okay? But these are the kind of things that you have to do. And the reason I put them all up is I need them all to work together. So I need to take all these distinct technologies and kind of have them all matched. And at the moment, many groups are working on individual components or 1 or 2, but how do they all come together? So let's put these all together. And this is just kind of showing part of the problem with the traditional repeater networks. And these kind of networks we call purify and swap, okay? And other ones, we also call these the first generation, but generate many pairs, purify, swap, purify on the longer range, swap, purify on the longer range, swap. And at every step in here, there's classical communication. So that is an interesting question. Do I want to use matter memories at all? Do I want matter-based repeaters, matter-based systems, or do I want all photonic? I don't know. There are advantages in both. So trapped ions, NV centers, ensemble memories, good storage, local computation. Some of them have problems interfacing with photons. Photonic quantum networks, photons in fiber-free space, long distance, low decoherence, challenges, synchronization, photon loss, generating single photons. Maybe I combine a little bit of both. I mean, people are thinking about all of these kind of ideas at the moment. Relays versus repeaters. I did promise I would get to this. If I have something in here that doesn't have any purification, my probability of success, my fidelity, the quality that comes out has an exponential scaling. In the classical world, repeaters stop exponential scalings. In the quantum world, maybe they don't, okay, but in the classical world they do. So in terms of hardware, there's almost no difference between running relays and running repeaters. The question is whether I have this extra purification step in there, okay? That purification step means you have to have better memories and various things like this, but really in the first generation repeaters and the relays look very similar. Both of them require entanglement distribution and various things like this. So just be careful, okay? And now what I'll say, first generation repeaters are good toys, but a warning. And I don't give many warnings. Some work we did a while ago with people like Yas Omar in Portugal and various things like this. We looked at these larger scale, purification and swap networks, and you get to a certain size, as your network grows, the performance gets worse and worse and worse, correct? But these repeated networks, these purified swap networks, have an interesting feature, okay? Get to a certain size and they explode. Add one more node and your network blows apart, and you can't generate entanglement between two arbitrary parties. Does that matter if I'm only wanting a metropolitan network or a network only within the UK? Maybe that's fine. But if I want a global network based on these first generation repeaters, I have a problem. I know ways around the stuff that we did here, okay? I can get around this, but it's costly. So really, just to summarize, as you know, quantum repeaters are very different than classical repeaters. We really need to think about what we want these devices to do and make sure that we design them to do a variety of applications. And what applications may I want repeaters for? So QKD is obviously one. Distributed computation, Shard and Rod were talking about. Any other applications? What else can I do with quantum repeaters? Clock synchronization, quantum remote sensing. Potentially, there's some cryptographic protocols now where you want 3 or 4 multi-parties. There's a whole series of these, and they all require slightly different things. Okay, this is what made me go grey. Okay, it's not universal about what the requirements are. So what this means is that as we're doing the design, I don't want system designs where I can do the first 1 or 2, but the 3rd or 4th go away in a sense, okay? And I think I should stop there. Questions or dinner, or both. They don't tell me anything. I think today is bento boxes, I think. I don't think it's a buffet like we had last night, but it's bento boxes? I have no idea. So our boss is not here at the moment, so. But just to emphasize, I mean, thinking about the design of your repeaters, okay, is critical for the development of the field. And while all of you are doing little different pieces, really think about what the system design is coming forward. Don't forget about classical communication, okay? Don't assume that your state, you can generate perfect bell states. As a theorist, we love perfect bell states, okay? They're really, really nice, but they don't happen in the lab. We don't have Werner states in the lab, okay? We don't have mixes of two bell states. But if I have a state where there's an asymmetry, okay, it's mainly rank 2 with a little bit of the other two, we know purification protocols that can exploit that, and so that you can save resources. So wherever you can, design well.
There's one more issue that we actually assume that repeaters are trusted nodes.
Yep.
In the actual network scenario, when it will become a global internet,
I don't assume trust here at all.
even though the detectors are at the
Don't care. This is like a measurement device independent scheme. The shear factor is, I'm going to generate entanglement between two end parties, okay? I trust no one, so I'm not going to generate one pair. I'm going to generate 10 pair, use one for the application I want, and use the other 9 to verify. So one of the nice things about repeaters, okay, is that we do not trust the intermediate nodes. If the intermediate nodes cheat, okay, which I do, then you won't get the bell, then at the end, you won't get the bell pair out. So one of the things that we've got in all these protocols, and we've seen people talking about it here, is that we need to do verification. You need to be checking continuously what's going on here, okay? In the random number generators, we did this, we had a certification verification program, but in networks, we're going to have to generate some resources and just check, is this what we expect it is, okay? Because, I mean, I'm a very mean person, and I've actually done this live at one stage by accident. I was working in my backyard for a while, and I put a spade down and chopped one of the country's fiber cables. 140 cores. Whoops. Evidently, I wasn't meant to be digging there, but the signs were in Japanese. So, I mean, we've got to check. So basically, one of the things about teleportation, these intermediate nodes we don't have to trust, but you have to verify. If you can trust all the nodes, okay, if I can really trust all the nodes, I probably still want to verify anyway, in case there's been an error in a sense. But we really want to get to the stage here where our internet providers who give us this entanglement, we don't have to say, we don't have to believe what they're saying. We can check. Saying that, so I'm telling you now that given I've generated entanglement, once I've got that entangled pair, and I can verify it's a bell state, I can then use it to teleport any quantum state between you and me, okay? And these evil people in the middle can't read it, okay? So does quantum automatically mean we have security? No. The design helps. So it depends on the design. So one of the things that I'll talk to you in the next lecture is I'll talk about some of the more advanced repeaters, which we call the second and third generation, where potentially I improve speed, but I remove security. And I may have to bring security back in. So security comes when I have a bell pair, because the bell pair has no information. But maybe I don't want to send bell pairs, create bell pairs. Maybe I want to do direct quantum messaging, okay? So there's a whole series of fun to be had here in a sense. But I believe my next lecture is next week, so you have to wait a week. Further questions? Food, dinner? Yeah.
So you told us that it will be here by 7.
I think it's 7, okay. I'm hungry. No, so please do go and have a look on the website and download slides and various things like this. Okay, so that's, one of the things is that we teach, all of us who are teaching you are going through large amounts of material, and that's why looking at the slides afterwards is handy, in a sense, or beforehand. So next week, I think my 2 lectures are, one is on the 2nd and 3rd generation repeaters, and then after that, it's a little bit more on network design principles, aggregation, multiplexing,